Continuation to the previous lectures, in this lecture also we are going to see some more examples on metric spaces. Here the set that we consider is the set of all complex numbers, and metric was defined to be the usual metric that we define on the set of real numbers, that is absolute value of the difference of two complex numbers. Here these two entries are taken from set of complex numbers, therefore your x1 can be written as x1 plus iy1, where x1 and y1 are real entries. Similarly, z2 can be written as x2 plus iy2. Here these two entries are reals. Now, what is absolute of z1 minus z2? It is nothing but x1 plus iy1 minus x2 plus iy2, and this is defined. This is x1 minus x2 plus I times of y1 minus y2, and the absolute value on the complex numbers is defined to be under root x1 minus x2 whole square plus y1 minus y2 whole square. Now if you closely look at it, this is the metric that we define on R2, right? So there we have taken x and y from R2, and this x was x1 x2 and y was y1 y2. There what we had absolute sign. But what bothers if we have absolute sign or do not have absolute sign? Because we are making a square of distance, so it is going to be the same. Okay. Since this is coming to this form, using the same idea that we proved for this case, we can say this is also a metric, and with this metric the set of all complex numbers forms a metric space. Next, I am going to state the names for these spaces. We have proved this is a metric on Rn, and this can be proved to be a metric on Cn as well. Okay, what is this Rn and Cn? Rn we have encountered in many of the previous videos. This Cn is going to consist of Z1, Z2, Z3, and it goes on till Zn. Okay, where all these Zi are taken from C, which means all the entries are complex numbers. If these has to be expressed in terms of the real numbers, in the sense it will be of the form x1 x2 and it goes on till xn plus I times of y1 y2 and it goes on till yn, where this xj, since we have I here, we represent this by xj, and this yj are taken from reals. Okay, this is going to be the case, and this can be proved to be the metric on Rn as well as on Cn. With this metric only, we are calling this Rn as Euclidean space. Okay, and we are going to call the Cn as unitary space. Okay, and now we are going to restrict our case to something, that is on R we are going to talk. Okay, on R, when you define a metric in this form, that is absolute of x minus y, we have proved this is a metric, and we have proved this as the semi-metric. And when you have something like this for a positive integer, okay, when you have something like this, what is it going to be? It is going to be a metric for some cases, and it is going to be semi-metric for other cases. That is, when your k is an odd value, okay, then your d of xy is a metric. Okay, be it any odd value, it will turn to be a metric. When k is even, your d of xy is going to be a semi-metric. Now with the same thing, let us apply this to set of all complex numbers. When applying this to a set of all complex numbers, we will have this is going to be a metric only when k is 1. Okay. For all other k values, it is going to be semi-metric. Because whenever we are trying to prove this is a metric or semi-metric, the only problem that we will encounter is d of xy equals 0 implies what? Okay. Generally, okay, let us have x power k is same as that of y power k. Okay, when it is considered in reals, it will be here we may also say that we have 1 times of y power k, and based on the roots of this one only we will have single value or many value. If it is real, it can be either plus or minus 1, but when it is complex, we have second roots of unity, third roots of unity, fourth roots of unity, and we have many more. That is why it is not turning to be a metric except for k equals 1. Thank you.